Still Serving Veterans is a nonprofit that provides veterans with no-cost services that help position them in quality, meaningful civilian careers, navigate and access their VA benefits, and make the best of their time after service. We've included links to their website if you'd like to learn more, as well as a donation link if you'd like to help support their work. Beyond donations, as they're mostly grant-funded, they always need more veterans using their services. So if you are or know of a U.S. military veteran who could use any of the services you see here, we've included the contact info of the Chief Programs Officer, Jim King, in the description, and you can reach out to him directly to learn more, or if you'd like to refer a friend. Thank you, Still Serving Veterans, for helping our bravest men and women stay resilient together.
Hello, my name is Alaiya Tuntemeke-Winter. I am an applications engineer at Orolia Defense and Security. Today, I will be giving a webinar called Preparing the Warfighter for Advanced GPS Environments Through Simulation. In this demo and webinar, we will talk about the importance of resilient PNT. We will define and outline jamming and spoofing risk to the warfighter. We will talk about real examples of jamming and spoofing, as well as how to test your products for PNT resiliency. We will do a demonstration that will show how our receivers are affected when they are being jammed and spoofed, and then we will talk about finding the right simulator for the right use cases. We will also talk about some other methods to ensure resilient PNT for the warfighter, and then we will have time for some questions. So the importance of resilient PNT is the convergence of traditional PNT and non-traditional PNT technology to improve reliability, performance, and safety of mission-critical applications. Resilience offers trusted real-time location and information by protecting, authenticating, and offering alternatives to existing PNT sources, such as GNSS. The operational impact of resilience is the ability to detect vulnerabilities in your GPS receivers, such as jamming and spoofing incidents. You need to be able to issue alerts and provide alternative sources of navigation and positioning. In systems where the smallest discrepancies in data accuracy, availability, and stability can result in system outages, crashes, or worse, loss of life, it is imperative that we do not fail. So, what is jamming and spoofing? Jamming is often conflated with interference, but GNSS jamming is typically thought of as jamming by means of radio frequency signal, while interference is sometimes used in the context of natural causes, such as atmospheric phenomena or obstacles. The interference could cause accidental or intentional. However, either way, it inhibits the GPS receiver's ability to extract GPS signal information from the background noise, preventing the receivers from being able to give accurate data. One example of this is about 10 years ago, the New Jersey airport was experiencing intermittent failure on their system. They had a system for landing and taking off, and this system, though being new, was struggling to determine why it was being taken down. In the end, the cause was a GPS jammer. This jammer was being used by a contractor to block his company's vehicle fleet tracking system. Unbeknownst to him, his small $30 device plugged into the lighter port of his vehicle was also affecting the airport's highly sophisticated state-of-the-art system in the process. Though spoofers are banned now in the US, this is a perfect example of what these jammers can do and the importance of being prepared for these incidents. In a case where somebody was being malicious, this could affect the warfighter immensely. Spoofing is the act of broadcasting fake signals with the intent of deceiving a GNSS receiver into accepting the false signals as genuine. From a technical perspective, spoofing GNSS retrievers is more challenging than jamming, but the consequences are more severe because the receiver actually uses these manipulated signals for PNT calculations. Neither the system nor the operator may realize that the indicated PNT data has been corrupted. Spoofing is not an easy undertaking, especially when you are targeting a moving target, but it has been done and the threat is considered real and growing. A couple of years ago, people used spoofing in an internet game to cheat at Pokemon Go. This is kind of an innocent and fun example of how spoofing worked. In the game, you needed to go to specific locations to catch certain Pokemon, and users were spoofing their phone to travel the world to catch Pokemon on islands and deserts that they might not be able to actually reach physically. In this example, this is pretty harmless. However, in a more alarming instance, last year, research was done by Bjorn Bergman of SkyTruth, and he found several ships in various parts of the world reporting locations thousands of miles away from their location. He even discovered one boat that was reporting locations almost 1,000 miles inland in Utah. A craft that is relying on GPS could be displaced without knowing their true location for days at a time. If we have a ship that is relying on GPS in order to navigate for our missions, they could be lost and not know that they are lost until it is too late. Our systems are also reliant on GPS for time. So if the receivers latch onto a spoofed time, it will make syncing with other units or systems near impossible. In the world today, we are seeing more and more instances of jamming and spoofing. Our systems are also more and more reliant on GPS and GNSS to operate. It is imperative that we know how our systems will react in these situations. Are your systems easily taken down by these incidents? Will the safeguards that you have in place trigger when they are supposed to? And do the secondary systems work correctly? These are questions that can be addressed before even encountering the obstacles using simulation in the lab. Before the warfighter encounters situations that jamming and spoofing could put them into trouble, it is good to know how our systems will react. Threats are getting easier to deploy and they happen more frequently. It's no longer a matter of if, but when. One vital aspect of resilient PNT is to test PNT equipment for its actual vulnerability against jamming and spoofing. This involves the process of continuous improvement through threat replication in the lab to innovate and adopt new detection and mitigation strategies. Threats such as jamming and spoofing can be replicated in the lab through GNSS simulators and test how your receiver will react in spoofing and jamming situations. This way, you can either elevate existing mitigating strategies or add in new ones. The test objective is to harden PNT systems by understanding how your receivers will work in those scenarios, and then implementing mitigation techniques and testing and modifying and improving them continuously. In this demo, we are going to simulate a scenario with one jammer and one spoofer. This scenario will emulate a possible incident the warfighter could face. We will be using the 4U Broadsim and a commercial receiver for this demo. Using this tool, you can create scenarios with multiple jammers and spoofers, but for this demo, we will keep it simple with one of each. So let's jump right into Skydel and create our scenario. First, we will open up a new configuration, and then we will add our radios. Our current platform supports the DEC DTA2115B. I will add 4 of these radios. On our first radio, we will select our GNSS output signals. We will choose GPS L1 and Galileo E1. These will be our truth signals. We will set up radio 3 to be our interference output. Here we can see our interference group is group 1. If we choose this box and then we select the signals we are using, the tool will automatically select our central frequency for us. Next, we will open up a spoofing instance. To do this, we will click this button at the top and then choose Skydel Instances. We will open up a spoofer instance. In this instance, we only have one choice here, which is spoofer, so we'll add our spoofer. We can see that each spoofer has a group number. That group number should be the same one that we assign to our interference radio. We will choose our signals again, Galileo and GPS, to match our truth signals. In our spoofing instance, we can leverage the full toolkit that you may be familiar with from the main configuration, such as custom start times, custom vehicle trajectories, and pseudo ranges. Next, we will configure our spoofer instance. To do this, we will go back to the main instance and click on Spoofers under Settings. Here we will add a spoofer. In the General tab, we can change the name of our spoofer, and we can enable and disable it. For now, we will disable it. We will enable it later during our simulation. We change our reference power. We're going to change it to 2 dBm. And then there are some other advanced options here as well, but we are going to leave those alone for this demo. In the Signal tab, you can see the address, which refers to the IP address that we are using to talk to the spoofer instance. We will also see the status, which we would like to see connected for this. And then here in the output section, everything else we need to know about the GNSS signals being output is displayed. This little green indicator means that we have configured our spoofer correctly. If it's yellow or red, that would mean that there was an issue with the way that we have configured our spoofer, such as too low of a sampling rate or incorrect center frequency. Those error messages would be indicated here as well. Next, we will go to our trajectory in the Trajectory tab. We will add our trajectory. For our spoofer position, we can choose fixed, circular, hardware in the loop, or track playback. For this scenario, we are going to choose a fixed location. So I will input that now. Our location is going to be in California, right off the Golden Gate Bridge. One way spoofers might attempt to trick receivers is on a boat off of the coast. So this is how we will attempt to trap our receiver. In our Antenna tab, we can choose the antenna pattern. We are going to choose the default for this demo. However, you can input your own custom patterns as well. In this Antenna tab, you can also apply an offset to your antenna or change the attitude. Now that we are done configuring our spoofer transmitter, we will configure our knockout jammer. To do this, we will go back to the settings and choose the Interference tab, then add a dynamic transmitter. A dynamic transmitter allows us to better simulate a more real-world transmitter. During our simulation, we will be able to see the power change as our receiver gets closer to our transmitter. Our transmitter will also be in Group 1, which is the same interference group that our spoofer is in. We are going to change our reference power to 5 dBm. We will add the signal type AWGN and give it a bandwidth of 3 MHz. Under our Trajectory tab, we are going to also make this one a fixed trajectory. I will input those coordinates again. These coordinates will be in California. Once input, we can see our red dot. This is our transmitter. In this case, it is just off the Golden Gate Bridge. Next, we will change our start time. Generally, we want our start time to be in the future because that will make our receiver happy. So we will choose 2022. Currently, it is March, so June works for us. Lastly, for our truth instance, we will choose a trajectory. For this, we will choose a vehicle simulation, and we will choose a KML file. This is a KML file that was previously created and saved on the machine. An easy way to create these KML files is using Google Maps. Our truth trajectory goes down the Golden Gate Bridge and then splits off and goes east. I will also change the speed to 80 kilometers per hour and then click Finish. And that's it for our truth instance. So now we will finish up configuring our spoofer instance. We will only have a few more things to configure in our spoofer instance. In the spoofer instance, first we will want our start time to match our truth instance. So we will change this date to 2022 to match. Next, we will assign the spoof signal. In our vehicle tab under body, we will use a vehicle simulation. We will select edit and then import a KML file, just like we did for our truth instance. We will select the file here and choose our spoofing trajectory. This trajectory will follow the same path as our truth trajectory until it gets to this split. Then it will continue south. We will change our speed to 80 kilometers per hour so that it matches our truth instance. And that wraps up our spoofer configuration. The last thing we need to do before beginning our simulation is connect our receiver. I have a U-Blocks receiver connected to the Broadsim via USB. I will select this port and change the baud rate to 115/200. The Broadsim will read the NMEA data from our receiver. It will use this data to plot the receiver on our map, and we will see more information in this tab to our right. We can see up the top that we are streaming RF data. We can also see the time. And in our Spectrums tab, we can see our truth GNSS signals, GPS and Galileo. In our interference graph, we can see our knockout jammer transmitter and our spoofer. It says no signal because we have disabled it in our configuration. The reason we have disabled it is so that we can make sure that our receiver is tracking our truth GNSS at the beginning of our simulation. Once our receiver gets a little closer to the transmitter, then we'll turn on the spoofer. Taking a look on the right side of the map, we can see more information about our signal, our receiver, transmitter, and our spoofer. We can also see here that the spoofer is disabled. We can see the reference power at our transmitter to our receiver. As our receiver gets closer and closer, the transmitter will see this level rising. When we click on our Constellations tab, we can look at GPS or Galileo. When we click Show Receiver, we can see what satellites the receiver is tracking. We will let our receiver get a little bit closer to our transmitter and watch the effect. This simulation is taking place in San Francisco, but it could be simulated anywhere. As we are getting closer, we can see the signal quality degrading. We'll zoom in a little bit to see a closer view. Once we start to see the SVs in this display drop out, then we're going to pop over and enable our spoofer. As the satellites are beginning to degrade rapidly, this is a good time to turn on our spoofer to hopefully catch our receiver. To do this, we'll go to Settings in our main instance. Then go to Spoofers, and in Spoofer 1, we can enable our spoofer. We will pop back over to the map, and on the right we can see our spoofer signal is now active. We can also see our power at the reference, which is -110 dBm. Now that we have moved away from our transmitter, we can see that our receiver is again tracking more SVs.
Since our spoofer and our truth are going on the same path at 80 kilometers per hour, we can't quite tell which one the receiver is following yet until we get to the split. If we look at the deviation, we can see how far our receiver got away from truth. As we got closer to our transmitter, in our spectrums tab, we can see that the spoofer is active. As well as our deviation tab, we can continue to observe how far the receiver gets from the truth. While we wait for our receivers to reach the split, we can address the effects that this could potentially have on the warfighter. At this point in the scenario, we are still on what we believe is our charted course. Since we watched the SVs drop out, we know that there was a potential problem, but we seem to be back on course now. Without being warned that your receiver was jammed and now potentially spoofed, the warfighter would be unable to take evasive actions against this attack. So as we approach the split, we'll be able to see whether or not the receiver continues east with the truth or if it turns south, which means it is following our spoofed signal. All right, moment of truth here. It looks like they are diverging. Yes, so it appears the receiver is going south, which means it has been captured by the spoofer. We will let the scenario play out, but at this point we have clearly been tricked. Without knowing that the receiver is being spoofed, we could be headed not only in the wrong direction, but a dangerous one. In this scenario, we are maybe ending up a few miles from where we were hoping to end up. However, in a real-life scenario with potential malicious intent, a spoofer could disrupt a mission, split up a convoy, or lure us into an area we would rather not be in. Knowing the way your system is going to react in a scenario like this could be the difference between arriving safely, mission complete, or a failure.
So being able to simulate your scenarios is important to the resilience of your system. We can see that by not being able to control or know how our receivers are going to react, how they're going to be able to react, we don't know how we can counter these situations. So we at Orolia have a line of GNSS simulators ranging from our Solo or our GSG 5s and 6s that are small and able to be at your desk. So you can create simple scenarios, you can do ad hoc testing, you can do simple development, and you can even do some plugin development as well, which I'll mention plugins later, all at your desk before you even move into the lab, so that you can maximize your efficiency and maximize your use of your GNSS simulators. So I have my Solo today. I also have a GSG 8. So our GSG 8 also runs on that same Skydell platform that we just showed in the demo. This platform grows with you, so you can be using the same Skydell platform at your desk with your Broadsim Solo, and then you can move into the lab and you can be using it on your GSG 8 or your Broadsim, or if you are doing more complicated testing, in your anechoic or wavefront. So we have our GSG 8 and our Broadsim that are great for complex scenarios, formal testing, jamming and spoofing testing as well, as you saw, and our wavefront scenarios that we can do SERPA testing and different antenna testing as well. So it's important to choose the right simulator for your use case and to choose the right combination of simulators for your use case as well. Some additional features that come on the Broadsim platform, you can also model other things. So we don't only face regular interference or malicious interference. We also have interference just from mountains that we're crossing or dips. So in the Broadsim platform, we also are doing terrain modeling as well, so that you can simulate those types of things and their effect on your systems, as well as alternative forms of navigation. So you can test how either maybe your secondary system, when you lose GPS, then how does the secondary system work? And is that working as expected? And does your system switch to that? On our Broadsim platform, we can also simulate encrypted codes like M code and Y code that you may be seeing. We have IMU data for our IMU plugins for when you have to switch. Again, if your GPS is bad and you need to start using your IMU, you can simulate that stuff as well. We also have hardware in the loop, so you can test your systems that way, as well as an open plugins or open source plugin framework. So if the Broadsim doesn't have specifically what you think you would like to simulate, there are also plugin features. So you can develop your own plugin features, and they will integrate into the Broadsim simulation engine user interface. So things like IMU, a barometer, a wheel tick, or other PNT sensors that you have, those are great examples of things that you could develop in a plugin environment. The IMU and other plugins such as Terrain plugin already exist, and there are examples provided or can be provided to you by Orolia in the Skydell platform. However, it is important to have simulation. Simulation doesn't cover everything. R-PNT really comes from a layered approach. One thing is not going to be the thing that makes you prepared to face these situations. So Orolia offers a layered approach to resilient PNT. We have our external references. So as our system's coming in, we can use things like a broad sense nano that would maybe detect that you are seeing GPS jamming or spoofing. Also, we have things that are M code and Y code that can ingest your encrypted signals as well. There are also layers of antennas. So we provide things like anti-jamming antennas that can prevent the bad signals from ever even entering your system. There are inline protections as well, such as broad shield. One thing I said was very important was being able to not only sense when you're being jammed or spoofed, but to be able to warn your system and then do something about it. So Broad Shield offers those inline protections that will let your system know when it's seeing jamming or spoofing, or a broad sense that can be wired into your system as well. Jamming and spoofing detection is important because when you know that you're being jammed and spoofed, you can then do something about it. So using tools like Broad Shield, you can switch to other internal PNT references. So no matter what you're using for your inline protection, it's important to be able to switch to IMU or alternative forms of navigation or other things that you might use like a wheel tick, and knowing when it is important to switch to those internal references. We also have internal quality detection built into our products. So in our baseline capabilities, we know if we are losing PNT, maybe we have a complete outage and we're not seeing it anymore, so we're not getting the PPS that we think we should be getting, or we're not seeing the signals we think we should be seeing. There are checks for that as well in our baseline products that we provide for timing and positioning. So PNT has become integral to our world's infrastructure and to our warfighter. Resilient PNT is the best way to prepare and protect these PNT systems to keep them operating at peak efficiency. Although the dangers of jamming and spoofing are more prevalent in the world today, the ability to detect vulnerabilities in GPS, such as jamming and spoofing incidents, gives us the ability to issue alerts and provide alternate sources of navigation and positioning to keep the mission-critical systems online. Through thorough testing of your system in the lab before they encounter these scenarios, through simulation, you can give the confidence that your systems will work in the field. Are there any questions?
If you'd like to ask any questions, there's a tab on the right for questions. You can click on that and type your question in for Alaiya. We don't have any so far. We also have a polls tab. There'll be 2 polls in there. One asking how long it takes you to create your jamming and spoofing simulations with your current tools. And then a second one, if you're interested in discussing your simulation application with our team, you can just click yes to that and we'll be in touch. Doesn't look like we have any questions, so give it just another couple seconds.
Okay, so other things that we can simulate with our plugins as well is we have started to work with simulating cislunar as well. So already built into our simulations, we can simulate orbital scenarios as well. We can also do many other jammers and spoofers, although in our demo we only did one. There is the ability to do multiple jammers and spoofers. There's the ability to do multipath and things like that as well. So most scenarios that we can think of that our warfighter would encounter, we have built into these simulation systems. Cool. All right, well, if there are no questions, I will wrap it up. There is another webinar tomorrow, so we hope to see you tomorrow at Defense Days again.
Can you explain the terrain simulation as part of testing?
Yes. So our terrain simulation, this is an additional plugin that you can add into the Broadsim. Right now it is in specific locations, but it can be expanded to other locations as well. It allows for, if you have maybe a jammer that is on the horizon, but there is a mountain in the way, it would simulate how that mountain would affect where your vehicle is. So when you're going, behind a large obstacle, you wouldn't see as much power from that, or from other transmissions as well, maybe from different satellites. You might be blocked. Another good example of that are like a canyon where you would not be able to see, you wouldn't be able to get good data coming into the canyon because you'd be blocked by those walls. But the terrain plugin allows you to simulate that kind of situation in your scenarios as well. So it accounts a little bit more for the topical terrain.
And do you offer the ability for a user-defined spoof detection to fuse with your own?
For a user-defined. I'm not sure that I understand
Another question actually related to terrain came in too. Do you take into account multipath from the terrain?
Yes, we do include multipath, and that's actually already in Broadsim, even without the plugin, as we account for multipath to account for things like urban canyons and things like that. But multipath is used in the terrain plugin.
And can you simulate buildings?
I'm not sure yet how many buildings we've simulated. I would have to check on exactly how far we are in specific cities and things like that. But terrain itself can be simulated. So using a plugin, maybe not the current terrain plugin, you could definitely simulate buildings.
All right.
And I don't know. There was the other question, but I don't know if I saw it.
Do you offer the ability for a user-defined spoof detection to fuse with your own? I'm not sure.
I'm not sure exactly what you mean by a user-defined spoof detection. I know that you can define the different antennas, the different gains, the detection itself. I'm not sure. I think that you could integrate your receiver into our system, so you could do your hardware in the loop, and then you could see whether or not your system was detecting jamming and spoofing.
All right. That about does it for questions.
All right. Well, thank you very much.